Hello, this is an introduction to Chapter 18, Confidence Intervals for Proportions. Now, I do want you to read through this chapter, but I want to highlight some of the main points. And so the author starts off with a really nice introduction to the idea of confidence intervals using sea fans here. So here's a picture of a sea fan. They live in the coral reefs. In this particular example, they're coral reefs off the coast of the Yucatan Peninsula in Mexico. And these particular sea fans, the population of the sea fans, which there could be millions of these along the Yucatan Peninsula, but this particular population of sea fans is suffering from a disease called, and there's background in here that you can read about, but the disease is called aspergillosis. All right, so the question is, what percentage of these sea fans in those coral reefs off the Yucatan Peninsula have this disease? And the population could be millions of sea fans, and so the researchers don't have the time, money, and resources to check every single sea fan on the ocean floor. And so, what people usually do is, when your population is so big, you take a random sample. And so they did that. They took a random sample, and here's the results right here. It says they took a random sample of 104 sea fans right here. And out of those 104 sea fans, it turned out that 54 of them had this disease. All right, so what does that mean about the population of all the millions of sea fans in the world, or in the Yucatan Peninsula? So let's go here, get a blank piece of paper. So your population, all sea fans in the coral reefs off the coast of the Yucatan Peninsula, and the question, what proportion of this population have this disease called aspergillosis? All right, now, in other words, we want to know, what is P? The population proportion. P equals what? All right, now here's what we know. From the random sample, we know our sample size N was 104. We know P hat, or we can calculate P hat. It says there was 54, right here, 54 out of 104 have this disease. So in some homework questions and examples, they just tell you the percentage. On this one, we got to calculate the percentage ourselves. And so 54, the number of quote-unquote successes, in this case, success is that the fan has a disease, which I know doesn't really seem like a success, but it's just an arbitrary labeling. So 54 divided by 104 equals 0.51923. I'll just round this to 51.9%, or 0.519. Okay, so that's what we know from the sample. Now, what else do we know? Well, from the last chapter 17, with sampling distributions, we know that even though we don't know what the real population percentage is, we know that whatever it is, the sample result is probably, assuming it's an unbiased sample and so on and so forth, the real percentage of sick sea fans in the entire coral reef community off the coast of Yucatan Peninsula, whatever that real percentage is, it's probably somewhat close to 51.9%, because we know from the simulations we've done and so forth in the last chapter that most samples are somewhat close. In fact, we can quantify it. We can say 95% of samples are within 2 standard deviations of the real percentage, whatever it is. But here's where it's different. In the last chapter, you always knew P. That they would say, suppose that 30% of people are left-handed or something. What's your distribution of your samples look like? Here we're turning it around. Which is the more realistic situation? P is unknown because we don't know the percentage of the whole population, but we have a particular sample that we can go on. All right. Now, in the last chapter, here's what we also knew. We knew the standard deviation the standard deviation of the sampling distribution. I know it's a huge mouthful. We're going to introduce new vocabulary in a minute here, but the standard deviation of the sampling distribution of all possible values of p hats, of which 0.519 is just one possible result. If we took another sample of 104, we would get something else, maybe 54% or 48% or something like that. But all samples will be somewhat close to the real percentage. Anyways, the standard deviation of the sampling distribution of all possible values of p hats can be computed by that super cool formula you learned about in the last chapter. Square root p cubed divided by n. Okay, now this is p hat. That's a little hat there. Okay, so that's great. And in the last chapter, all you did, you knew your p, you plug it in. You do 1 minus p, get the q, you plug it in, divide by n, and there you go. You've got your standard deviation. And then you can say, okay, 95% of samples will be within 2 of those standard deviations of the real percentage. But we have a little problem here, don't we? What's p? Well, we don't know. That's the whole point of doing the sample in the first place, is to try to figure out what p is. So we don't know exactly what p is, and so we will not know exactly what this standard deviation of the sampling distribution is going to be. However, we have a pretty decent approximation, because we also know from chapter 17 that your sample, in this case 0.519, my sample portion, is somewhat close to the real percentage, and it's going to be off by maybe 4 or 5 percentage points in most cases, and so here's what we can do: is we can estimate the standard deviation with this formula: p hat times q hat divided by n square root. Okay, that's no problem. We've got p hat right here. P hat is just the percentage of successes in the sample, 0.519. Q hat, you can probably guess what that means. It's the percentage of failures, in this case, the percentage of CFANs that do not have the disease, which is just 1 minus p hat, 1 minus 0.519, which would be, let's see, that's 0.4, what is that, 81. Okay, and n, we know n. N is 104. All right, so just plug those numbers in. So 0.519 times 0.481 divided by 104, take the square root. Okay, well, let's see what we get here. So calculator time, press clear. So 0.519 times 0.481 equals 0.249. Divide that by 104. We get 0.002. Take the square root. Okay, 0.04899. Let's just round that to 0.049. Okay, so that's an estimate of the standard deviation of the sampling distribution of all possible values of p hat. Okay, which is a huge mouthful. And so instead of saying this 0.049 is a standard deviation of a sampling distribution, blah, 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 instead of saying that huge mouthful, we will have a new name for this. We call that the standard error. Okay. So the definition of standard error is it's an estimate. So it's an estimate using a sample result. The estimate using a sample result, in this case p hat, and q hat, but that just comes from p hat. An estimate of the standard deviation, I'm going to abbreviate standard deviation, just SD, of the sampling distribution. Okay, and the formula, instead of PQ over N, it's P hat, Q hat over N square root. So we need to use the word, or the phrase, standard error to remind ourselves it's just an estimate of the standard deviation, of the real standard deviation. of the sampling distribution, because we're not going to know. We're never going to know what that is. Okay, now, if you're feeling kind of guilty or worried about not knowing the exact standard deviation, it turns out to be okay. So let's just suppose here for a minute that the real percentage, let's say that this p hat was off by, say, 7 percentage points, and let's say the real percentage of diseased sea fans off the coast of Yucatan Peninsula, let's just suppose it's 0.45 instead, which would be about as far off as you would expect from a sample size of 104. So let's just suppose that was the real percentage, and let's say that Q then would be 0.55. So if you plug that into the real formula, PQ over N square root, you get 0.45 times 0.55 divided by 104. That was our N. Now, of course, we don't know what P really is, but this is just supposing here. So let's do this calculation. Let's see what we get. So 0.45 times 0.55 is 0.2475. Divide by 104. Okay, 0.023, take the square root. Okay, look, it's still 0.0, it's 0.0487. If you round it to 3 digits, it's the same. Right there. And so it turns out that's why using p hat in almost all cases is going to give you a very, very good estimate of the real standard deviation. But we still call it standard error just to remind ourselves. Okay, so still we'll use the 0.049 right there. Okay, now having said all that, we can now, based just on our sample, here's what we know. We know that the sampling distribution, whatever that is a normal curve. We don't know the exact nature of the sampling distribution because we don't know P, do we? But whatever P is, let's say P is 45%. Whatever P is, that's in the middle of that sampling distribution. So we can't actually sketch the actual sampling distribution here, but here's what we can do is, based on our knowledge of the normal curve, we can say this. We can say that 95% of samples will be within 2 standard deviations. But now I'm going to use the word standard errors instead, because the standard error will, in almost all cases, will be very, very close to the standard deviation anyways. So 95% of samples will be within 2 standard errors of P, the real percentage of the population, that's the goal. That's the whole point of doing a sample in the first place, is try to figure out what P is. Okay, this is a very, very powerful statement right there. So all we have is a sample, but we know that the sample is close, and we can quantify how close. 2 standard errors close, at least 95% of the time it will be. All right, so that brings us to the idea of margin of error. Okay, so here's what you can do is you can take the 0.049, which we computed already, times it by 2 to get 2 standard errors, and you get 0.098. And so now you can say that 95% of samples will be within 2 standard errors, 0.098 of the real percentage. Okay, which means then that, now we don't know what the real percentage is, but we do have a sample, which was, what was it, 0.519 was the sample. You take plus or minus 0.098, and you can say that that sample has a 95% chance of being within 0.098 or 9.8% of the real percentage right there. And so we have a name for this. This is called the margin of error. Okay, now the next video will go into more details about how precisely, because you don't always times by 2, because sometimes you don't want to be 95, sometimes you need to be like 99%. So the next video we'll discuss that.